This course is for anybody who wants to understand multi-degree of freedom structural dynamics. The course is built around the theme of seismic analysis and determining the response of structures to earthquake-induced ground motion. But in reality, that's just one form of excitation. And once you complete this course, you'll be able to analyze structures experiencing ground motion or directly applied dynamic loads, such as wind loading or blast loading, for example. Now, as you move through the course, you're going to be developing your understanding of the underlying theory, but at each stage, you're going to implement what you learn using Python. This is a really great way of bringing the theory to life, and it's a fantastic way to learn structural dynamics. The course culminates in you developing your own code for the analysis of a multi-storey structure subject to ground motion. The final code will be capable of handling anything from a 2-storey to a 200-storey structure. But more important than the code itself is the fact that you'll understand how every single line of that code works and why it works and specifically what it's doing, because you'll have written it from start to finish. Now, this means you're going to have no problem further developing the code or customizing the code beyond this course when you go and use what you learn on your own projects. The next section kicks off with us looking at some of the fundamental topics and fundamental ideas in the context of single degree of freedom systems first. We'll start by developing some analytical solutions to harmonic ground motion, but we'll quickly move on to looking at realistic ground motion and developing numerical solutions to tackle these problems. So this section of the course is really focused on plugging some of the gaps in our knowledge around the behavior of single degree of freedom systems, and also covering some of the fundamental theory and concepts around earthquake-induced ground motion. So in section 3, we introduced multi-degree of freedom systems, and in particular our shear building dynamic model that we're going to use as our test bed throughout this course. We'll discuss the coupled nature of these multi-degree of freedom systems and what makes them a challenge to solve. We'll explore numerical solutions to the coupled equations of motion by developing our own central difference algorithm, and then we're going to look at some off-the-shelf solution toolboxes that we can use. In section 4, we're going to cover, by far, in my opinion, the most important part of this course, the most important topic in the course, and that is modal analysis. We're going to spend plenty of time here to make sure that you really understand concepts like orthogonality, mode shapes, and what it means to uncouple the equations of motion. You're going to see that the modal approach to solving a dynamic problem really offers us some great advantages over direct integration of the equations of motion that we saw in the previous section. So by the end of this section, you're going to have a really deep understanding of modal analysis, the advantages that it offers us, and you're going to be comfortable applying it independently yourself on your own projects. In section 5, we're going to deal with damping. Now, in this section, we'll see that the uncoupling of the mass and stiffness matrix that we discussed in the previous section can't be directly applied to the damping matrix. So in this section, we're going to look at how we can derive a damping matrix that delivers prescribable and predictable levels of damping in each vibration mode. This is quite a short section, but it's going to be really important in making sure that you have two solution strategies for your dynamic systems: a direct integration solution strategy and a modal solution strategy. It's really important that you can apply both strategies to solving dynamic problems, because both have different strengths and weaknesses. And so we're going to finish out this section by demonstrating the equivalence of both of these different strategies. In the final section of the course, you are going to take everything that you've learned up until this point and build out your final analysis code, or your capstone project for this course. Now, at this point, you'll understand the theory really well. You'll understand how to map that theory over into your Python code. So in this section of the course, we can really focus on writing a set of codes that will scale well, that can analyze anything from that 2-storey to that 200-storey structure. So it's really all about scaling what we know in this final section of the course. So by the time you finish this course, you'll have a toolbox full of analysis codes, and you'll have the knowledge and confidence to apply them independently on your own projects.